All right, now we're going to look at some theorems. In fact, we're going to look at three of them that are really important before we continue on looking at extreme values and graphs. Um, they have several uses. So one of them, one way these theorems are used, we can use them to estimate the error when we use linear approximation. When we approximate a curve by a line, and it'll estimate our error. It will explain the first derivative test, which we haven't done yet. It explains why the derivative of a constant is 0. And it helps us find extreme value. Maxes and mins. Okay, so the first theorem we're going to look at, I'll just say theorem 1. Okay, first off, f is defined on an open interval. If f takes on an extreme value, that means a max or a min, at C and at any point in AB, and f prime at that point exists, then f prime of C equals 0. Okay, you have to remember that C is an interior point. It's between A and B. It's not at the endpoints. Okay, so for something like this is a min, so that's an extreme value because it has a horizontal tangent line. So f prime equals 0. This is C, this is A, this is B. Okay, this is a max, but f prime is not 0 here. It has to be in the interior between A and B. But we don't look at the endpoints. So this theorem is for extreme values in the interior of an interval. Okay, now we're not talking about sharp points, because at a sharp point, f prime does not exist. And notice in our hypothesis, we have to have the derivative existing. So we're not talking about sharp points being an extrema in this case, because f prime exists. So wherever f prime exists on this interval, then for the maxes and mins, you're going to have a horizontal tangent line. Okay, the opposite of this is not true. Which says if f prime of C equals 0, this does not mean there is an extreme value. So for an example of that, you let f of x be x cubed, you take the derivative, set it equal to 0, that gives you x equals 0 or c equals 0. But if you graph x cubed, there's a horizontal tangent line, but not a max or a min at 0. So f prime at 0 equals 0, but we have a horizontal tangent line, which is not a max or a min. Okay, so that's really, really important. Let's look at the next theorem, and I'll show you what all this is good for, what we need all this for. Next theorem is Theorem 2. First question, well, before I get to this, I won't state the theorem yet. Here's a question. Do you agree that if a car travels 210 miles in 3 hours, at some point its speedometer must read 70 miles per hour? Okay, well, why is that so? Well, rate is distance over time, and the distance is 210 over 3. So this is the average rate should be 70. Now, to be the average, at some point, you could be going 80 or you could be going 60, and then in between somewhere you're going to have to pass through 70. That's just an illustration. But if the average speed is 70, that means you could be going a little faster, a little slower at the time, but you can't be going slower than 70 all the time, and you can't go above 70 all the time, or the average would be higher. So this has to do with Theorem 2. At some point, it has to get to the average. Okay, Theorem 2. F has to be continuous. On a closed interval AB, and differentiable on an open interval AB, then the derivative at some point is going to have to equal the average. So this is saying the instantaneous velocity at some point between A and B, the instantaneous velocity has to equal the average velocity, which we saw up above. At some point it has to be going 70 if the average is 70. And also remember, this is the slope of the tangent line at x equals c, and this is the slope of the secant between A and B. So let's draw a picture. We might have a picture like this, where we have, here's A, here's B, and here's the function. And let's say that C is right there. Here's their tangent line. This is C, and that's parallel. These two slopes are equal. This is M, and this is M. If they're parallel, your slopes are equal. So at some point, your slope of your secant has to equal the slope of the tangent. Okay, but, or that's saying the tangent line is parallel to the secant line. If the slopes are the same, you have parallel lines. All right, but that's a good illustration too with the distance and the time. All right, let's look at an example. Say f of x is 2x squared plus x plus 1 from negative 2 to 3. It's continuous. Okay, make sure you're always checking your hypothesis. That's really, really important. If something doesn't work in the hypothesis, then your conclusion is going to be wrong. This is a polynomial, and you should know the shape of it. It's a parabola, so that's continuous. It's differentiable. You have to check. Really on the whole real numbers, because f prime of x is 4x plus 1. And so let's say f prime at c is 4c plus 1, and f of b minus fa over b minus a is f of 3 minus f of negative 2 over 3 minus a negative 2. So plugging in 3 into the function, I get 18 plus 4 is 22. A negative 2 is 8 minus 6 plus 1 is 7 all over 5. And that's 3. So at some point, 3 is going to have to equal 4c plus 1. So c is going to equal a half. And c is in the interval minus 2, 3. So make sure you always check that your point that you find is in the interval they give you. So drawing the picture, at negative 2, I have 7. At 3, I have 22. This is a parabola. At 1/2, say here, this is m, the slope of the secant line. Let's see. And this is m here. That's the tangent line at x equal 1/2. So they're parallel. If I do the picture, I think you could see that they're more parallel. Okay, another thing you should know about this is c cannot be found algebraically all the time. I mean, that means by doing algebra. The importance is that it exists. Okay, so here's another example. Let's talk about a straight highway, 50 miles long. Connects A and B. Prove that it is possible to travel from A to B by car in 1 hour without the speedometer reading 50 miles per hour. Okay, so what we have, let's say this is distance and this is time, and we're going to start out at 0, 0, and the slope of the secant line is the change in distance over the change in time between 50 miles per hour in 1 hour, so 1 hour. Okay, so on this, let's say we're going to graph this. It's 1 hour 50 went 50 miles. So in 1 hour it went 50 miles. Oh, I should have said it's impossible. Sorry. Let me leave that red. I didn't even... It's impossible to travel. So it has to reach 50. So if your average rate is 50, then at some point the instantaneous, which is also the instantaneous, velocity is going to have to equal 50 miles per hour at some point by this theorem too. So it's like your car could be just, the speed of it could just be going like this, but there are going to have to be a couple places where if the average is 50, then you will have to be going 50 miles an hour at some point. Because it's a continuous function. So if you take your test scores and your average is 50, that doesn't mean you made 50 on one of the tests, because that's not a continuous function. Your test scores are just points, not connected. But with distance and rate and time, that is a continuous function. You're connected there. So that's why this works here. Another example. Why must the derivative equal 0 for some x between 0 and 1? Well, if we do the average, f of 1 is 0, f of 0 is 0, and that's equal to f prime of c at some point between 0 and 1, at some point c between 0 and 1. So f prime of c equals 0 by theorem 2. Okay, now, before I go on, theorem 2 has an important name. It's called the mean value theorem. And that should make sense, because what does the word mean mean? It means average. So this theorem, where f is continuous on a closed interval, f is differentiable on an open interval, there's some point where the slope of the tangent line equals the slope of the secant line, or the derivative is equal to the average rate, or the instantaneous velocity is equal to the average velocity at some point. That's importantly called the mean value theorem. Okay, now our last theorem is called Rolle's theorem. That's theorem 3. It's a special case of the mean value theorem. Okay, first off, let f of A equal f of B. This is where your endpoints are equal in the mean value theorem. So if you do that, if your endpoints are equal, you have Rolle's theorem. So it's just a special case. And again, let's repeat the cases, the hypothesis. F is continuous on a closed interval. F is differentiable on an open interval. Then there is at least one C such that f prime of C equals f of B minus f of A over B minus A, but that's equal to 0 since f of B equals f of A in this case. So there's a place where f prime is equal to 0. That means it has a horizontal tangent line. Okay, so here's an example of that. Here is f of x is x cubed minus x in the interval -1, 1. F of -1 equals -1 plus 1, which is 0. F of 1 is 1 minus 1, which is 0. So these two are equal. F is continuous because it's a polynomial. So it's continuous everywhere, and it's x cubed, it looks like that. And f is differentiable because f prime, well, you can take the derivative, and it's a nice and smooth curve. So we have all the conditions are met for Rolle's theorem, and it's really important that you go through the hypothesis for all your homework problems and check that. So f prime of C is 3c squared minus 1. There's a point where that's equal to 0. That's what the theorem says. So C is plus or minus square root of 3, square root of 1/3, which is plus or minus square root of 3 over 3. Now you got to check, see which ones are in -1, 1. Make sure you check that. And in this case, both are in the interval -1, 1. So you got to check that. So what's happening here? Let me just draw a quick picture. Suppose it looks like that. Just suppose that that's the case, and here's your endpoints. It's saying that there's 2 points where you have horizontal tangent lines within that interval. Okay, so this is where the horizontal tangent lines exist. Okay, one more example. If f of x is 5 plus 3 x minus 1 to the 2/3, f of 0, and say 0, 2, f of 0 is 5 plus 3, which is 8, and f of 2 is 5 plus 3, which is 8. So these are equal. But f prime of C, the derivative, is never 0 for any C, and 0, 2. Well, why doesn't it contradict the theorem? Well, it doesn't, because if you take, okay, first off, is f is continuous? Well, f is 5 plus 3, and it's the cubed root of x minus 1 squared. So as long as you're squaring that, that's going to give us a positive. So we can always take the cubed root of a positive. You can take a cubed root of a negative too, but this is no problem. This is continuous everywhere. If you take the derivative, though, is it differentiable? What happens when you take the derivative? Bring the 2/3 down. Alright, sorry for the interruption. Let's finish this problem. But you can see if we take the derivative, that's equal to 5. Oh, that's wrong. Derivative 5, 0. And there's no way that this is equal to 0, because there's no way you can have 0 in your numerator. Remember, if a fraction is equal to 0, you have to be able to have the numerator equal to 0. So that's never 0. So here's the problem. You can take the derivative, but f is not differentiable. That derivative doesn't exist at 1 because it'll make your denominator 0. F is not differentiable at x equal 1. And 1 is between 0 and 2. That's our interval 0, 2. So that's why it doesn't contradict it, because one of the hypotheses is not satisfied. F is not differentiable, and it has to be differentiable for every point in the interval. And it's not. It's not differentiable at 1 because it's undefined at 1. Right here, if you look at this, this is f prime is undefined because it makes 0 in the denominator at x equal 1. You can't have 0 in your denominator. Okay, so look at some of the homework problems, and I hope that helps, and sorry for the interruption.